Section: Introduction. In this section, we recognize that the research community is increasingly valuing long context modeling as an essential feature for future large language models. This is driven by various real-world applications, such as deep reasoning, code generation, and multi-turn autonomous systems. Recent advancements, like OpenAI's O-series models and others, allow models to handle entire codebases and lengthy documents while maintaining coherent conversations and performing complex reasoning. However, we face challenges with traditional attention mechanisms, which become a significant latency issue as the sequence length grows. Estimates suggest that attention computation can account for a large portion of total latency when dealing with long contexts, highlighting the need for more efficient attention methods. A promising approach is to leverage the natural sparsity of softmax attention, where selectively computing important query key pairs can lower computational costs without sacrificing performance. We see that recent strategies, such as KV cache eviction and blockwise selection methods, show potential in this area. Yet, many existing sparse attention methods do not perform as well in practice, often failing to deliver the expected speed improvements and primarily focusing on inference without adequate training time support. To overcome these challenges, we identify two key areas that need attention. First, we need hardware-aligned inference speedup, which requires designing algorithms that work well with hardware during both the prefilling and decoding stages. Second, we need training-aware algorithm design to ensure that we can train models efficiently while maintaining performance. To address these needs, we introduce NSA, a natively trainable sparse attention architecture that incorporates hierarchical token modeling. NSA reduces computation per query by organizing keys and values into blocks and processing them through different attention paths. We also implement specialized kernels to enhance practical efficiency. NSA brings two main innovations. It optimizes blockwise sparse attention for better hardware utilization and ensures stable end-to-end training through efficient algorithms. We evaluate NSA through extensive experiments on real-world language data, pre-training on a large transformer model and assessing its performance across various evaluations. Our results show that NSA matches or exceeds the performance of full attention models while providing significant speed improvements, especially for longer sequences. We also reflect on modern sparse attention methods, which have made progress in reducing computational complexity but often only apply sparsity during inference. This can lead to architectural biases that limit their effectiveness. We analyze these limitations, particularly the challenges of phase-restricted sparsity and incompatibility with advanced attention architectures. Many methods struggle to achieve meaningful latency reductions, prompting us to develop algorithms that effectively combine advanced architectures with efficient implementations to fully utilize sparsity for improved model efficiency. Section Summary. In this section, we highlight the importance of long context modeling for large language models and discuss the limitations of current sparse attention methods, which often fail to translate theoretical efficiency into practical speedups during inference. We introduce our natively trainable sparse attention (NSA) architecture, designed to optimize both hardware utilization and training efficiency, demonstrating significant improvements in performance and speed across various tasks compared to existing approaches. Section: The Myth of Trainable Sparsity. In this section, we explore the concept of native trainable sparse attention, driven by two main insights from our analysis of inference-only methods. First, we notice that applying sparsity after training can harm performance. Specifically, when we only use the top 20% of attention, it only accounts for 70% of the total attention scores. This makes certain structures in pre-trained models, like retrieval heads, susceptible to being pruned during inference. Second, we recognize the need for efficient training of long sequences, which is essential for developing modern large language models, LLMs. This involves pre-training on longer documents to improve model capacity and adapting through long context fine-tuning and reinforcement learning. However, current sparse attention methods mainly focus on inference, leaving training challenges largely unaddressed. This gap limits our ability to create more effective long context models through efficient training. We also face challenges when trying to adapt existing sparse attention methods for training. For instance, some methods use discrete operations, like clustering, which disrupt the flow of gradients during the token selection process. This makes it hard for the model to learn the best sparse patterns. Additionally, some theoretically trainable methods encounter practical inefficiencies. For example, the token selection strategy in methods like hash attention requires accessing many individual tokens from memory, which disrupts efficient memory access and reduces training efficiency. Given these limitations, we see a strong need to redesign sparse attention mechanisms. We propose a new framework called Native Sparse Attention (NSA) that aims to improve both computational efficiency and training effectiveness. In the following sections, we will outline the algorithmic design and implementation of NSA. Our methodology includes both algorithm design and kernel optimization. We will first provide background information on our approach, then present the overall NSA framework, followed by its key components, and finally, we will describe our hardware-optimized kernel design for maximum efficiency. In the background, we note that the attention mechanism is crucial in language modeling. Each query token calculates relevance scores against all previous key tokens to produce a weighted sum of value tokens. As the sequence length increases, the attention computation becomes a significant part of the overall computational cost, especially for long contexts. We also discuss arithmetic intensity, which is the ratio of computation to memory access. This ratio influences how we optimize algorithms for hardware. Each GPU has a critical arithmetic intensity based on its compute capability and memory bandwidth. For tasks like causal self-attention, training and prefilling phases are compute-bound, while autoregressive decoding is memory-bound, leading to different optimization goals. To harness the potential of attention with natural sparse patterns, we suggest replacing the original key-value pairs with a more compact and information-rich set based on each query. We define the optimized attention output using dynamically constructed key-value pairs. We can create various mapping strategies for these pairs, which include compression, selection, and sliding window techniques. We maintain a high sparsity ratio by ensuring that the number of remapped keys and values is much smaller than the total sequence length. Section Summary. In this section, we highlight the limitations of existing sparse attention methods, which primarily focus on inference and fail to address training efficiency, leading to performance degradation and non-trainable components. To overcome these challenges, we propose a natively sparse attention framework, NSA, that enhances computational efficiency and training viability by dynamically constructing optimized key-value pairs based on the current query. Section: Algorithm Design. In this section, we present the design of our remapping strategies, which include token compression, token selection, and a sliding window approach. For token compression, we combine sequential blocks of keys or values into block-level representations. This allows us to create compressed keys and values that summarize the entire block's information. We define the compressed key representation based on the block length, the stride between blocks, and a learnable model that maps the keys in a block to a single compressed key. We typically choose a stride that is shorter than the block length to reduce information loss. The compressed representations help capture broader semantic information and lessen the computational load during attention calculations. In terms of token selection, we recognize that using only compressed keys and values may overlook important details. Therefore, we implement an efficient mechanism to identify and retain the most relevant tokens with minimal computational cost. Our selection strategy processes key and value sequences in continuous blocks, which is beneficial for hardware efficiency and aligns with the distribution patterns of attention scores. This blockwise selection is essential for optimizing performance on modern GPUs, as they handle continuous block accesses more effectively than random reads. We first divide the sequences into selection blocks and assign importance scores to each block to determine which ones are most critical for attention computation. To compute these importance scores, we utilize the intermediate attention scores generated during the compression token calculations. If the sizes of the compression and selection blocks match, we can directly use the attention scores. If they differ, we derive the importance scores based on their spatial relationships. For models that share key value caches across query heads, we ensure consistent block selection to minimize cache loading during decoding. After calculating the selection block importance scores, we retain the top blocks based on these scores. The selected keys and values then contribute to the attention computation. For the sliding window approach, we address the challenge that local patterns can dominate the learning process. We introduce a separate sliding window branch that focuses on recent tokens, allowing the other branches to concentrate on their specific features. We maintain recent tokens in a defined window and isolate the attention computations of different information sources into distinct branches. The outputs from these branches are combined through a learned gating mechanism. By providing independent keys and values for each branch, we stabilize learning and prevent interference between local and long-range pattern recognition. In summary, after obtaining all three categories of keys and values, we compute the final attention output, completing our algorithmic framework for NSA. Section Summary. In this section, we introduce our remapping strategies, which include token compression to aggregate information into block-level representations, token selection to preserve relevant keys and values efficiently, and a sliding window mechanism to manage local context. These strategies work together to enhance attention computation while minimizing computational overhead and preventing gradient interference. Section: Kernel Design. In this section, we focus on kernel design to achieve speed comparable to flash attention during training and prefilling. We implement hardware-aligned sparse attention kernels using Triton. Since multi-head attention, MHA, is memory-heavy and not efficient for decoding, we concentrate on architectures with shared key value, KV, caches, like grouped query attention, GQA, and mixture of experts, MO, which are aligned with the latest large language models, LLMs. While compression and sliding window attention can work with existing FLASHATTENTION2 kernels, we introduce a specialized kernel for sparse selection attention. If we were to use flash attention's method of loading continuous query blocks into SRAM, it would lead to inefficient memory access because queries in a block might need different KV blocks. To solve this, we optimize by grouping queries differently. For each position in the query sequence, we load all query heads in a GQA group, which share the same sparse KV blocks, into SRAM. Our kernel architecture has several key features. 1. Group-centric data loading. For each inner loop, we load all queries from the group at a specific position and their shared sparse KV block indices. 2. Shared KV fetching. In the inner loop, we sequentially load continuous KV blocks into SRAM to reduce memory loading. 3. Outer loop on grid. Since the inner loop length is similar for different query blocks, we organize query output loops in Triton's grid scheduler to optimize the kernel. This design enhances arithmetic efficiency by reducing unnecessary KV transfers and balancing workloads across GPU multiprocessors. We evaluate our new sparse attention NSA method from three perspectives: general benchmark performance, long context benchmark performance, and chain of thought reasoning performance, comparing it to the full attention baseline and other leading sparse attention methods. We will discuss the efficiency of our sparse computation in a later section. For our pre-training setup, we follow the standard practices in advanced LLMs, using a model that combines GQA and MO, with a total of 27 billion parameters and 3 billion active parameters. The model has 30 layers and a hidden dimension of 2,560. We configured GQA with 4 groups and 64 attention heads, setting the dimensions for queries, keys, and values accordingly. For MO, we use a structure with 72 routed experts and 2 shared experts, selecting the top 6 experts. To maintain training stability, we replace the MO in the first layer with a multi-layer perceptron, MLP. We set specific parameters for NSA, including compression block size, sliding stride, selected block size, and window size. Both full attention and sparse attention models are pre-trained on a large dataset, followed by fine-tuning for long context adaptation. We ensure both models are trained to full convergence for a fair comparison. Our results show that NSA consistently outperforms the full attention model. In addition to comparing with full attention, we assess several leading sparse attention methods, which compute full attention scores and select the top scores for each query. These methods cover various sparse attention strategies. For general evaluations, where most samples fit within the local context window, these methods perform similarly to full attention. Therefore, we primarily present comparisons between NSA and full attention in this context. In long context evaluations, we compare across all baseline methods, ensuring equal sparsity for a fair assessment. For chain-of-thought reasoning evaluations, we limit our comparisons to full attention, as sparse attention methods do not support training. Section Summary. In this section, we describe our implementation of hardware-aligned sparse attention kernels using Triton to achieve significant speedups in training and decoding, focusing on architectures with shared KV caches. We introduce a specialized kernel design that optimizes memory access through group-centric data loading and shared KV fetching, while also detailing our experimental setup and comparisons with state-of-the-art attention methods, demonstrating the effectiveness of our approach. Section: Performance Comparison. In this section, we evaluate the performance of the pre-trained NSA and the full attention baseline using a variety of benchmarks that test knowledge, reasoning, and coding skills, such as MMLU, GSM-8K, and Human Eval. Our findings, presented in the evaluation table, show that NSA outperforms all baselines, including full attention, on 7 out of 9 metrics, despite its sparse nature. This suggests that while NSA may not fully utilize its efficiency on shorter sequences, it still performs well overall. Notably, NSA excels in reasoning tasks, indicating that our pre-training helps models develop effective attention mechanisms by focusing on the most relevant information and filtering out unnecessary noise. This consistent performance across different evaluations highlights NSA's robustness as a versatile architecture. For long context evaluation, we find that NSA achieves perfect accuracy in a 64K context test, thanks to our hierarchical sparse attention design. This design uses compression tokens for efficient global context scanning and selection tokens for precise local information retrieval. The coarse-grained compression identifies relevant context blocks with low computational cost, while token-level attention ensures that critical details are preserved. We also compare NSA to other sparse attention methods and the full attention baseline on long bench, maintaining a consistent token activation of 2,560 across all models. Our results show that NSA achieves the highest average score, outperforming all baselines. This improvement is due to our native sparse attention design, which allows for end-to-end optimization and synchronization between the sparse attention module and other components, as well as the hierarchical mechanism that balances local and global processing. In the chain-of-thought reasoning evaluation, we assess NSA's ability to learn mathematical reasoning through post-training. We use knowledge distillation from DeepSeek R1 and conduct supervised fine-tuning with a large dataset of mathematical reasoning traces. We compare NSA-R, our sparse variant, with full attention R on the American Invitational Mathematics Examination benchmark. Our results indicate that NSA-R significantly outperforms full attention R in both 8K and 16K context settings, demonstrating the advantages of native sparse attention in capturing long-range dependencies and maintaining context density for deeper reasoning. Finally, we analyze the computational efficiency of NSA against full attention on an 8-GPU A100 system, configuring the model with specific parameters to ensure a fair comparison. Section Summary. In this section, we evaluated the performance of the pre-trained NSA model against the full attention baseline across various benchmarks, finding that NSA outperformed all baselines in 7 out of 9 metrics, particularly excelling in reasoning tasks. Additionally, Our hierarchical sparse attention design enabled NSA to achieve high accuracy in long context scenarios and demonstrated significant improvements in mathematical reasoning tasks, confirming its efficiency and effectiveness in handling complex challenges. Section: Training Speed. In this section, we compare the speed of our Triton-based NSA attention and full attention implementations with Triton-based FLASHATTENTION2 to ensure a fair evaluation. Our NSA shows increasing speed advantages as the context length grows, achieving up to 9 times faster for forward operations and 6 times faster for backward operations at a context length of 64,000. This improvement is more noticeable with longer sequences, thanks to our algorithm design that aligns with hardware for better efficiency in sparse attention. Specifically, we utilize a blockwise memory access pattern to enhance tensor core usage and optimize loop scheduling to reduce unnecessary key value transfers. For decoding speed, we find that the memory access bottleneck, linked to how much key value cache we load, primarily influences performance. During each decoding step, our NSA only needs to load a limited number of compression tokens, selected tokens, and neighbor tokens, which leads to a significant reduction in latency as the decoding length increases, achieving up to 11.6 times faster at a context length of 64,000. In our discussion, we reflect on the development of NSA and share insights from exploring various sparse attention strategies. While our approach yields promising results, we recognize the challenges faced with other strategies and analyze attention patterns to inform future research. We first address the difficulties we encountered with alternative token selection strategies that guided our design decisions, followed by visualizations that reveal attention distribution patterns. We initially looked into adapting existing sparse attention methods for training but faced several challenges. For instance, we examined clustering-based strategies like cluster KV, which store keys and values from the same cluster together. However, these methods introduce computational overhead from dynamic clustering, face optimization issues due to imbalances in execution times, and require periodic reclustering, all of which hinder their real-world effectiveness. We also considered other blockwise selection strategies, such as Quest and INFLLM, which compute importance scores for blocks and select the top blocks based on their similarity to queries. However, these methods struggle with non-differentiable selection operations that increase overhead and can degrade performance, as well as low recall rates from heuristic approaches. We evaluated these methods on a model with 3 billion parameters and found that both exhibited inferior loss compared to our NSA. To gain insights into transformer attention distributions, we visualized the attention map from our pre-trained 27 billion parameter full attention model. This visualization revealed blockwise clustering patterns, where nearby keys often had similar attention scores. This observation inspired our NSA design, suggesting that selecting key blocks based on their spatial continuity could enhance efficiency while maintaining high attention patterns. Finally, we review existing methods that improve attention computation efficiency through sparse attention, categorizing them into 3 groups: fixed sparse patterns, dynamic token pruning, and query-aware selection, and we introduce several representative works from each category. Section Summary. In this section, we compare the training and decoding speeds of our NSA attention with existing methods, demonstrating significant speedups, up to 9.0 times in training and 11.6 times in decoding at 64K context length, due to our efficient hardware-aligned algorithm design. We also discuss the challenges faced with alternative sparse attention strategies, which informed our design choices, and visualize attention patterns that suggest a promising approach of selecting key blocks based on spatial continuity. Section: Fixed Sparse Pattern. In this section, we discuss several strategies for improving attention mechanisms in processing long text streams. We start with fixed sparse pattern, where the sliding window method allows us to compute attention within a specific, limited area. Streaming LLM tackles the issue of handling lengthy text by keeping 2 key parts of the context: an attention sink, which consists of earlier tokens, and a local context window. While these methods help reduce memory and computation needs, Their fixed approach to ignoring broader contexts can hinder performance on tasks that require a complete understanding of the context. Next, we explore dynamic token pruning. H2O uses an adaptive technique to lower memory usage in the KV cache during decoding. This approach removes tokens that are considered less important for future predictions based on their recent usefulness as indicated by attention scores. Similarly, SnapKV employs a token pruning method that keeps only the most essential features, optimizing memory use. It identifies these important features through attention weight analysis and voting during the initial filling process, then updates the KV cache by merging selected compressed features with the latest context to ensure consistency in prompts. We also examine query-aware selection. Quest utilizes a blockwise selection method, estimating the importance of each chunk by calculating the product of the query and the minimum-maximum values of the key chunks. This scoring helps us choose the top important key value chunks for attention. INFLLM combines fixed patterns with retrieval techniques by maintaining attention sinks, local context, and retrievable chunks, selecting representative keys from each chunk to assess their importance. Hash attention treats the identification of key tokens as a recommendation problem, mapping queries and keys into a Hamming space using learned functions. Lastly, Cluster KV achieves sparsity by first clustering keys and then selecting the most relevant clusters for attention computation based on how similar they are to the query.